Inverse kinematics. So what the Jacobian does is it basically gives you the velocity, right? So velocity of some point is j times q dot, but the velocity is, let's call that dx dt equals j dq dt, where when I say capital X, it really means x is this vector x, small y. Okay, so 2D it's small x, small y, 3D will be x, y, z. So it's basically a vector. And what I can do is I can write this as dx equals j dq. Right? I can just eliminate time. So when we talk about inverse kinematics, we are given x and we are asked to compute q, right? Given the end effector position, we need to find the joint angles. So what we can do is we can take this expression and invert j. So j inverse dx. Okay. So what it's saying is that if you are at a certain location, your end effector is a certain location, and if you want the x to change, let's say you want to go up, right? So the end effector should move up. Then the Jacobian is telling you how much you need to change the angles dq such that you are able to go up. So what we do is we write dx as x ref minus x. This is your reference. Where do you want to go? This is your measurement. So where you are right now, your x and y coordinate. So you compute the difference between where you want to be minus where you are, multiply that with the inverse of the Jacobian, and so that will tell you by what angles you need to change the current position of the joint so that you are moving in that direction. So then what you do is once you get dq, you update q. Theta 1 as theta 1 plus dq1, that is write it in Python notation. So dq0 would be your zeroth component. Python index starts from 0. And then your new theta 2 would be theta 2 plus dq. Okay, I'm just assuming here I'm solving this problem for the manipulator, right? The one which you have done in the past. So it all boils down to this formula. Okay, what I need is xref, which is something you specify. I need the current position, which you know from the sensors, or in this case, you just get rid of the angles. And then this Jacobian is going to be the Jacobian of the end effector. Because that's the point you're trying to track. Okay, so what I'll do is I'll show you how to do this numerically, right? There's nothing to be done by hand. So every time I'll compute j. So let's say that the manipulator is, it's the same 2D example, two-link manipulator example. I know the position of the end. So I'll be able to compute the Jacobian, the end effector. I would know x because it's measured. X ref is something I want, and then I'll compute q, dq, and then proceed. How to use the symbolic toolbox. So what I did first was, before I did that programming to figure out the inverse kinematics, I just wrote some code which will give me the symbolic Jacobian. So I did these calculations by hand, but you can also do it symbolically. So for that pendulum, if you remember, let me just pull up the pendulum. So this is, okay, this is the pendulum. We have link O, P, and I think I called this E, which is missing here. Let's call that E. Okay, so remember that C1 is the position of G1 in frame 1, G2, C2 is the position of G2 in frame 2. And then I have lengths, L for the lengths, and theta1, theta2 is being the angles. So the code defines the values, the symbolic variables, theta1, theta2, c1, c2. And remember, this is the code to compute Jacobians. So I compute cosine sine. Remember, it was not trivial. It was 3 pi by 270 plus theta1. That's what I have here. I compute the homogeneous transformation. I do the same thing for frame 1 with respect to 2. Then I compute the transformation from frame 0 to 2. Then I get, so G11 would mean that, note here, first index means it is associated with that point. So I have G1 and G2, so there'll be G1 and G2. And then I use the second index to denote the frame. So the first one is in frame 1. That's why G1 underscore 1. That point is a distance of C1 along the x-axis. Then I compute G1 in frame 0, which uses the transformation. And the same too for 2. G2, 2, which is position of G2 in frame 2. Then I get with respect to frame 0 using H02. And then I'm also interested in this point E, which is the end effector. And I know the position of the end effector in frame 2, which is at a distance of L. And so I can use H02 to get that. So when I do this, I'll get a 3 by 1 vector, right? Because it has this one term. The number 1 in the last row, I delete that. And then I can, I'm just printing it. So Control Shift P. And so it gives me the expression which I can just copy paste wherever I want to. I have noted that I've used simplify. If I don't use simplify, this expression is slightly long. Just to shorten it, I use simplify. Okay, so given that, let's do the inverse kinematics. And I decided to use the same example, the circle. So okay, let's play this first, and then I'll talk a little bit about the code. Okay, so this is showing the tracking. The blue is, the red is the reference, and the blue is the distract. Okay, so I have here a function which computes the Jacobian. This is, by the way, a copy paste of the code generated from that earlier file. So I have to do it by hand. I have a code which does forward kinematics. This is again copied from the earlier code, which I showed you about forward kinematics. So given the joint angles, it basically sends me three things. It gives me the position of O, that is the end effector. This is the start, so 0, 0, point P, which is here. Actually, I called it Q here. This is also same as the end effector Q, or E and Q are the same here. So I can put a note here. Q is the same as E. Okay, and this is good because once I have this, I can use this for plotting as well as to do my IK. Okay, so then so that's my functions. I just need two functions, and there's a when I need to do the inverse kinematics, what I do is instead of starting, well, there's a problem here which was not in fsolve, which is in fsolve you could just define a curve, and then fsolve will put that manipulator right from the start to then the right position. Here is something which you need to do beforehand. You need to put the manipulator in the right position. If the manipulator doesn't start from the right place, then your solution will not look good because your expression for getting the inverse is based on that linearization, dj, dq, and that's only accurate for small displacements. So if you don't start the right place, then you could get some crazy behaviors. So I need to start the right place. So what I did was, instead of trying to give some random points for the circle, but you need to place the circle somewhere in the plane, right? I defined some angles. I figured out the end effector position. And then I said, this point is basically along the x-axis, along one of the starting points of the pendulum. So if there's a circle, it's that point, because I know that's the starting point. So it's placed that way. So you see that slightly, the reference points is based on the center, which is based on getting the forward kinematics, so getting the end effector position, Q, and then doing that. So it's just a way in which I can initialize it in the right way. I'll actually show you, if you don't initialize just in the right way, what happens. Okay, so that code initializes the pendulum, given the angles. Rather, I would say, given the position of the end effector to begin with, it initializes the curve. Okay, so it just puts the end effector in the right place. Then I get the Jacobian, I compute the inverse. Hopefully this is clear, Jacobian and inverse. I get the errors, which I talked about, x ref minus y, y ref minus y. Then I compute dx. Then I compute that correction, dq, j inverse dot x, which is just does the j times dx, j inverse times dx. Then I add to theta 1 that correction, dq0 and dq1. And then this is just a method to save the variables. I can do the plots. And then this code basically does the plotting. Okay, so we run this once more. Okay, so now what happens if I don't start the right place? Okay, so the example is, what if I just don't have this? Okay, so it'll be seen here. So it started here, and then it had to jump there. So it jumped here and then jumped there, and then went on. That's why I started in the right place. But in this case, it's okay. It's like it adjusts for itself. Only the initial plot is off, but then it gets back to the place. But if you have a different system, that's may not. I can't guarantee that will happen. It may be that it doesn't work well. It's also very sensitive to. It's also very sensitive to the step size. By step size, I mean I used from 0 to 2 pi. I use increments of 0.2. I think if I go say 0.5. It may not do, so you can see it doesn't do very well. That's because those points were further apart. That approximation doesn't really hold well. 0.8. At some point, it goes unstable. Okay. Now there's another thing which I think I'll make you do in the homework, which is correct for changes I made control. Where I put that radius correction. Let's go down. Okay, right here. Minus R. Minus R. Let's check if it works. Okay. Okay, it looks good. Okay, there's another thing which happens, which is this method relies on computing the inverse of the Jacobian. Okay, when you're taking any inverse in any computation, you need to be very careful about the inverse. The inverse sometimes is not defined. So there is a case when the inverse is not defined, and I think it will show up here. Let me just make this 0. And you see it just does crazy things. And that reason is because it turns out that there is a particular orientation where this Jacobian is singular. A singular Jacobian means that the determinant is 0. When that happens, the Jacobian inverse is not defined. When the Jacobian inverse is not defined, you cannot do this computation, right? This computation is meaningless because this is singular. Okay, so you should not have the manipulator in a singular configuration. You hear that many times when you talk with when people talk, they say that. The singular configuration for this manipulator is when the link 2 is at a 0 degrees. When that happens, that J inverse becomes singular. So it never start there. I think if you just change that to 0.1, it will work. I think here in this case, what happened was it was out of the work space of this. So it did not work because of that. Maybe if you change this to 0.25, it will work. Okay, let me bend this a little bit. Let me bend this a little bit more. That would be increasing this. That's 90 plus 60 is 150. I don't think that will work. So I don't think that will work here. maybe it is a singularity which shows up. I think it goes through, it starts off non-singular, but I think it goes to a singular position. So if you look at the histories of theta, you should see that. Let's try it with 0.5. I think it passes through the singularity right there. And that's why you have a problem, but it corrects for itself. Okay, let me keep it as this.